Here's an example of how a t-test might be used in a surveying application. Let's say we have two total stations that you're considering on buying. We'll call them total station A and B. And you're going to test them out, and you're going to take shots between two known points that have a known distance of 400.23 feet. You go out with total station A, you take 20 shots. You go out with total station B and you take 13 shots, and those shots are seen on your screen right there. So a t-test might say, well, which one would you buy, A or B, or would you buy both, or would you buy neither? Okay, and you're going to base this decision based on an alpha of 0.05, or a significance level of 0.05. What 0.05 is saying is that you are allowing the fact that you could have a chance of 1 in 20 of accepting the hypothesis that you should buy when in fact you really shouldn't buy. So the hypothesis is that the mean value of each sample, total station A and total station B, is not significantly different than the real population mean value of 400.23 feet. And this basically is a two-tailed test, because the significance difference could be either a significant difference of being higher, significantly higher than 400.23, or significantly lower than 400.23. So what we've done here is we've gone ahead and we know that there's 20 measurements for A, 13 measurements for B. We can calculate the descriptive statistics, like the mean value for the 20 shots that A took and the mean value for the 13 shots that B took. We can also calculate standard deviation for both A and B. For total station A, we're going to calculate the t-statistic by taking the mean value for all the A shots and basically comparing those to the mean value for, the total known distance between the 2 points. We're going to take the standard deviation, divide it by the number of shots squared. That's basically the standard error. And what you're going to find out is that your t-value is negative 1.87 almost. You're going to compare this value to the critical t-values based on the degree of freedom. The degree of freedom is the number of shots that you took minus 1. So basically for total station A, you have 19 degrees of freedom. Go to page 285, look at a degrees of freedom of 19, and you're going to find out that for the significance level that we've stated, 0.05, which again would be 0.025 in one tail, 0.025 in the other tail, that the critical t-value is 2.093. Since your calculated value of 1.869 or 1.87, negative 1.87, is not outside that, these the mean value that you've got for total station A, 400.18, is not statistically different than the population mean of 400.23. So I mean, basically what that's saying is that your critical t-value is right here, but your t-value is right here. So again, not statistically different. For total station B, we'll do the same thing. We will, using the mean value of all the shots with total station B and the population mean value that was given, we will use standard deviation divided by square root of n. Again, that would be called most of the times the standard error, and you'd come up with a t-value of negative 5.8. Now again, your degrees of freedom for this total station B, the shots, would be 12. It would be 13 minus 1. So you go to the back of the book and you'd pick out from the table a T critical value of about 2.18 or negative 2.18. Now this, your value here, does lie outside the critical T value. And what that says is that these shots taken with total station B are significantly different than the population mean or the mean distance between the 2 points. Basically, to show that graphically, here's the critical T value for the significance level that you've established, but here for total station B, here's the shots, and they lie way outside of this. So what this is telling you is that basically you would not want to buy total station B because this measurements just seem funny. Total station A, if you're going to buy one or the other, total station A would be the one that you'd buy.